In this teaching object, we're going to cover the topic of advanced buffers, which includes heap overruns and string format bugs. This topic is intended to be presented after the buffer overrun topic, as it uses many of those concepts as the fundamental basis for the topics we're going to cover here. We'll start off by covering heap overruns. The first question that comes up is, what exactly is a heap overrun? Well, if you've got familiarity with the stack overruns from the buffer overrun teaching object, you already have a good head start as to exactly how heap overruns work. The primary difference between stack overruns and heap overruns is that the heap overruns occur on the heap and typically require a little more ingenuity to exploit. Just like other buffer overruns, heap overruns need access to the execution stack or other parts of native memory in order to really take advantage of any kind of exploit. And in addition, the heap itself is typically an unmanaged construct. While it can be tough to find and exploit heap overruns, they're still possible. And so it's often easy to remember that while it might be less predictable to find an overrun on the heap, or it might be harder to leverage the pointers to pointers that are required in many cases, it's still possible, and there are motivated developers out there that would like to write malicious code to take advantage of systems if they can. So it's our responsibility as software developers to be aware of these potential overruns and to make sure that our code is clean of them. One of the most famous exploits of heap overrun bugs was the 2005 buffer overrun in the Windows JPEG processing. This was a very straightforward buffer overrun that just took advantage of a heap overrun in order to run malicious code on a machine. It has since been fixed and is now available on Windows Update in order to patch any existing Windows machines. But it's important to know that even in 2005, these things were still out there and still running wild. In your typical heap overrun, you'll find that there's really two primary places where you have to be concerned about when it comes to your stride analysis. The first one is the denial of service. As you can imagine, whenever you can overrun the stack or overrun the heap or overrun anywhere in memory with a buffer, it's pretty easy to reliably crash the target application. In fact, as long as you're able to overrun that buffer, you can almost be sure that even if the application doesn't crash, it's probably going to do something that it shouldn't be doing, may have corrupted data somewhere, or may end up down the road writing information somewhere that shouldn't be written. The second, and probably more dangerous of these two, is the elevation of privilege threat. As with buffer overruns of other types, the heap overrun enables a hacker to execute arbitrary code, which is always dangerous and always something that should be at the forefront of the mind of security developers. So let's start off by doing a little primer on allocating local memory. The local memory we're referring to here is the local memory of the process, as opposed to global memory, which would be managed by the operating system and could be shared between processes. In our case, talking about local memory, it's that it's allocated on the stack or on the heap. And you'll typically find that when you create memory, such as when you allocate variables on the stack, those are your inline variables or variables that are created in the function itself. Very rarely will you ever see something being newed and actually end up on the stack, with the exception of cases with the local alloc method. But newed or mallocked memory is allocated on the heap, and that's an important distinction, because a lot of times you will go ahead and you will create an object that's on the stack, and you will initialize it with an object that's on the heap. For example, in these three code samples we have two pointers there that are allocated on the stack. So those are execution stack, or rather, those are data stack pointers that are right around the same location as your return pointer and your parameters on the stack. And then in the same case we have with the class that you might allocate, that entire object, because it's not being newed, is allocated on the stack itself. However, those first two pointers are initialized to point to memory that's allocated on the heap, and you can tell by the malloc and the new, respectively. Now let's take a look at the heap in action from a conceptual point of view. We've got this simple foo function that takes in two parameters, and then it mallocs and news some memory, and it also points a buffer, a pointer at one buffer, and it does a couple string copies and so forth. And at the bottom, what we have is a sideways representation of the heap. So if we were to start at the left and move towards the right for heap allocation, you'd find that as we run through, the first character buffer is going to be allocated on the left side of the heap. Now note, this is the data referred to with the malloc 16 and not for the character pointer itself. That character pointer of buff is on the stack, whereas the malloc memory came from the heap. The next line of code will go ahead and we'll allocate a new character pointer, and that's not to scale because obviously it would be 1/4 the size of the buff data. The next line of code would go ahead and allocate another 16 bytes on the heap. And one of the things you'll notice is that unlike the stack, the heap memory is often allocated in blocks larger than asked for. And there's a combination of reasons for this, one of which is optimization, but it's important to keep in mind that you're not guaranteed to have one piece of memory right next to another piece of memory. So for the sake of people trying to exploit overruns on the heap, they have to keep that in mind, which gives an advantage to the security developer. However, it's not enough of an advantage to rely on. Now let's take the best case scenario for the code in this function. We can assume in the best case scenario that input 1 is a null terminated string that's less than 16 bytes. We can also assume that input 2 is a null terminated string less than 16 bytes. Now of course those are assumptions that you should never ever make in production development or even in practice or test development. But for the sake of the best case scenario, to show how the heap works, we'll run through this scenario. So now, since we have these two trusted pointers here, what we're going to do is we're going to step forward, and the next line of code will have one buffer pointer point at the second buffer. So that's just simply a pointer on the heap is pointing to a buffer on the heap. The next line of code is a string copy from the first input into the buffer that's first allocated. And now the second line of string copy code is going to do a copy into the redirected buff pointer, which is pointing at the same data that buff2 is pointing at, and copy the second parameter into that. Now this might seem like a complicated scenario, but this really lays the foundation for some stuff we're going to cover later when it comes down to potential heap overrun exploits. So now let's take a look at some of the heap in action at runtime. In this demo, we're going to take a look at the heap in action. We'll start off here inside one function, which will be the main focal point of this demo. There are 3 lines of code in here that allocate memory on the heap, and we're going to analyze the similarities and differences in the ways they get allocated by the heap at runtime. So you notice here we've got a character buffer that we're initializing with a 16-byte malloc array. We've got a character buffer pointer, which we're initializing using the new keyword, and then we've got a second 16-byte character buffer that's being allocated as our third variable there. So I'm going to start by going to the debug menu and hit start debugging, and what will happen is we'll hit our breakpoint here that's been set, and I'm going to go ahead and I'm going to step over this first line of code there so we can actually allocate memory. So you notice this value of buff, we're going to copy the name, and we'll just paste it up here and hit enter. And you'll see now we have a view in memory of what that area looks like. You see 16 bytes of CD memory indicating that it's been allocated in debug mode, and then 4 bytes of FD memory indicating the end of an allocation. Now, in debug mode here, we're able to take a look at some of the values that are set in place. For example, the address we're looking at in memory right now is 354F28. Now this is a value that is significantly different than our stack pointer, if we look over here, 12FD98, and also our instruction pointer being 4114A5. So you see that this heap memory is in a significantly different location than either the stack or the instruction memory. Now if we step over here and we go to our next line of code, you'll see that we've actually been moved a bit, but I'm going to move back up and see this is where our first buffer was allocated here. And if we scroll down a little bit, we can see right here an offset of what looks like 64 bytes is where they've put our next pointer here, our character pointer that's been allocated. And if we had to take a guess, I would probably say that our next memory will be allocated around here if we step through our next line of code. So I'm going to go ahead and do a quick step over for buff2. Now we go back up to buff, scroll down, we've got this value here that was the pointer for buff pointer, and then our allocated memory here at 354FB8. So we can tell because of the fact that the CD memory is all lined up here, leading with FD bytes and ending with FD bytes. Or we could mouse over the variable itself and see the 354FB8 in order to get that indication. Now there's a few things to keep in mind with the way the heap works. The first one is that you'll notice there's a bit of buffer space between one allocation and the next. Now this can vary widely depending on the runtime you're working, the operating system, possibly even the compilation options and so forth. In our case though, we know that there's a bit of a buffer space in between, so we have to keep that in mind when we're trying to defend against any kind of heap overruns that might occur in an application. So that's a quick view of how the heap works at runtime inside an application. Now that we've covered the best case scenario, let's cover the worst case scenario. This is when we deal with input 1 that's potentially more than 16 bytes long, and it probably not null terminated, or at least not null terminated within those 16 bytes. The second what if is what if input 1's buffer included a well-placed pointer to the execution stack. That means that if there was an address that was built directly into that buffer that was written to point at the return pointer of the execution stack, such that we'd be able to overwrite that if we were to put that value of the buffer into another pointer somewhere else. Now this might seem kind of complicated, but we'll circle back to it in a second. And finally, what if input 2's first 4 bytes contained a 32-byte pointer to another method? In other words, what if that pointed to a location somewhere that had arbitrary code that a malicious user might try to execute? So now that we're back at the reset point where we've allocated all of our memory, and we're going to have buff pointer point at buff2, which is fine. And then we're going to do this next line, which is an unbounded string copy that's going to end up overwriting the pointer in buff pointer to point at the return pointer that's currently on the stack. Now remember, we had talked about the end of that first buffer having a carefully placed address in it, and that address would happen to overwrite itself into the buff pointer space in memory. And now, when that last string copy occurs, that input 2 value, being the pointer to malicious code, would overwrite the return address on the stack, and as a result, when the method finished execution and went to return, we would find ourselves in a world of hurt. Typically with a heap overrun, if you're lucky, there will be an access violation error. Of course, this is still dangerous because it can result in denial of service against servers. If you're unlucky, you'll get instability, which is not only will you have the denial of service, but it'll be very difficult to debug because it may not occur all the time. And of course, if you're really unlucky, you'll find that the hacker is able to inject code into the process and then run it at the same privilege as the process itself. Now, of course, one way to mitigate this elevation of privilege threat is to go ahead and run with the principle of least privilege. However, even better would be to prevent the heap overruns in the first place. But as I mentioned, it's always a good practice to use the least privileged accounts required to run any given process. Now let's take a look at the worst case scenario in a heap overrun demo. This demo, we'll take a quick look at a simple heap overrun. This function foo is set up in a very similar way to the understanding the heap demo that we just did a few moments ago. In particular, we've got very similar variables that are being created in the same way on the heap. But you'll notice we also have a little bit of code in here. The first one is that we have our buff pointer point at the second buffer after it's been allocated. And then we go ahead and we do a copy of an input variable into the first buffer we have. And then finally, we do a copy of our second input variable into the second buffer we have. However, given the nature of the way our heap overrun works here, is that this copy here is going to be overwriting buffer so far that it overwrites our buff pointer, and this buff pointer ends up pointing at the return value, or rather the return instruction that's on the top of our stack. So let's set a breakpoint here. We're going to go ahead and we're going to start debugging, and we're going to let the application run, and you'll notice that we have our memory allocated. So if we take a look at this in our memory view, we've got the main buffer here, or buff1, we've got buff pointer here, and we scroll down a bit more, here is buff2. Now we'll step through some of the code here, and we could take a look and see what's being printed to the screen to give us more data. But if you see what we have for buff pointer, when we step over one line of code here, we're going to step over the line where it's being set, and you'll see that this is now pointing at this value here. We're going to step through a few more lines of code until we get to the offending string copy. Now, on this string copy here, remember, this is the buffer we're going to be copying into, which is only 16 bytes. And all the way down here, I believe this particular area is going to be pointing at the buffer pointer for buff2 that we're going to be using in a future string copy call. So if we go ahead and we step over this line of code, rather it goes to here, you'll see that this value has been written over here. And it's been written over such that this now points at the return instruction for the function we're currently in, so that it will overwrite that as soon as this function down here, this string copy, is called. So when this string copy is called, you'll see this has pointed over to look at our execution stack, and now if we keep running, you'll notice it's been redirected to go to this bar function that indicates that we've been hacked here. So in this case, we have an unfortunate set of events that has occurred in a heap overrun, which has taken advantage of the stack's return instruction pointer. It's kind of a complicated scenario to take advantage of, but it should be known that it is very possible for malicious users and hackers to take advantage of it. Now that we've covered some basic buffer overruns on the heap, let's talk about what happens when we work with classes and how even with using classes we can still be vulnerable to buffer overruns. Now typically with a class, when you develop the class, a lot of times there's an assumption that's made that the code and functionality inside that class really shouldn't impact things that run outside of that class. The term encapsulation defines that there is kind of a trusted boundary between a class and its caller and vice versa. Now, a couple things that are important to know when you're dealing with the heap is that the size of a class on the heap is the sum of the size of its members. Now, assume that a character pointer is going to be 4 bytes, or any other kind of pointer is going to be typically 4 bytes on a 32-bit machine. But in our case, we have this class here that has one method. There's an implied constructor as well, but the important thing is that methods don't take up space on a per-object basis. Methods are only allocated once with all their execution code, and then there's a virtual function pointer table that's used in order to reflect against the class to actually call the methods themselves. So in our case, when somebody allocates the myClass object, they're going to create a 18-byte object on the heap or on the stack. If you knew it, we will assume it's on the heap. Now you see the C first char is 1 byte, the SD buffer is 16 bytes, and C second char is going to be the 18th byte as a 1-byte character. It's also important to recognize that members typically align one after the other in memory in the order they are declared in the class definition. Now there are optimizing compilers that might change the order. There are ways you can potentially use pragmas in order to change the packing order, but for most cases, especially if you're running in debug mode where the compiler will not impact your code or the layout of your structures, you'll typically find that they'll run in the order that you've defined them in. Now let's take a look at the process of allocating a class on the heap. Similar to before, we're going to allocate memory on the blue heap below, running from left to right. When we allocate the class, you'll notice it allocates just enough space to hold all of the members in it. The dashed lines show the difference between the first character, the middle buffer, and the last character. After that, we allocate our character buffer pointer, and then we'll allocate a second buffer as well. Now, as you can see, we're going to lead into some more code here, and this code could potentially lead into some risks for us. So what we'll do is we'll now step into a demo for that. In this demo, we're going to take a look at a more complex heap overrun. The complexity of this heap overrun comes into play in that we're going to be using a class, and based on the way that class allocates memory on the heap, we're going to be showing how it could be taken advantage of in order to cause a stack instruction pointer to be overwritten, and then as a result a malicious user would be able to control the flow of execution. Now you see this code is very similar to the past few demos, except the difference is that instead of creating a 16 character buffer here, we're creating an instance of the myClass class. Now I'm going to scroll up a little bit here so we can take a look at the myClass definition. This is a very simple class. It has one character being the first char. It has a character buffer being 16 bytes in the middle, and then a second character ending it up. So the entire size of the myClass class is 18 bytes. Now you'll see in the constructor we set the first character to be 0, 1 and the second character to be FF. This is so the way we can easily track it down when we're looking at it in memory. There's only one method on this class, which is an unrestricted string copy. And as you could probably imagine, this is going to be the main target of a malicious user, in that they can see that whatever they can pass in as SC data will be written over this SC buffer. So I'm going to scroll back down into our foo function, and we're going to set a breakpoint right after the allocation of memory, and we're going to start debugging. And you'll see when the application comes up, we're going to point at pClass, and we're going to take a look at how that memory looks. Now I mentioned that there's 18 bytes that are allocated, which are this 18 right here. Now you see the 0, 1, which is that first character. You'll see 16 bytes of debug allocated buffer memory, and then you'll see the second character, which is the FF. Now if we go ahead and we're going to run the cursor here, we're going to see that we point to buffer 2. And pointing to buffer 2 is not a problem, because that's simply giving us a pointer to somewhere else for a future copy. And now it's this fill buffer class that we want to be very careful about. So if we'll run up to the cursor here. Now pointing at pClass, when we go to fill the buffer, what we have to watch out for is not only is it going to overflow those 16 bytes, it's going to overflow our extra character, and very likely will be architected to overflow all the way down until it fills up the return pointer of the method we're currently in. So let's say we continue running, we take one more step, and we can see that this buffer pointer, which would not be expected, has already been overwritten by that fill buffer method inside the class. So that class is actually writing the memory that it doesn't even own at this point. And then we will continue to run down until we get to the very end. And if we wanted to take a look at our current location in memory, what we would do is we'd say our pointer for buff our pClass is here. If we want to take a look at the actual address of the pointer, what we do is we give it the indicator, and this is actually our stack memory now. So we'll take a view here, and we've got stack memory, we've got other stuff, and right here is, I believe this would be our return instruction pointer. So when that string copy attacks, it's going to write over here, actually was our return pointer rather. That was just overwritten, so the way the next step in the code is going to be into this bar method that would be the malicious user had set up in order to be attacked. So this was a quick example of how using classes you could also be vulnerable to heap overruns without even realizing it. Now that we've taken a look at a few of the ways that heap overruns can cause headaches for developers, let's take a look at some of the practices that can help prevent heap overruns. To start off with, pretty much all of the buffer overrun practices still apply. You should continue to be wary of most string and memory copy methods. You should always use the GS switch, and of course use safe string handling routines where possible. And also, still as a big benefit is if you can use managed code, definitely take advantage of that. Managed code is virtually invulnerable to all forms of buffer overruns. Now the application verifier is a tool that we're going to cover because it provides ways for you to watch the heap among other things in order to make sure that your code isn't doing anything that could be risky. It's actually in the box with Visual C++ 2005 and requires one add-on that you can download. It's useful during the debugging process, but it should be important to keep in mind that it doesn't help at production runtime. So you run it while you're debugging your application, but it doesn't help once you've deployed it out to the field and have your customers using it. So you need to really pay attention during the debug process and really stretch your code to the limits, and the application verifier can help you find problems. So let's take a look at how this application verifier works at runtime. In this demo, we're going to take a look at application verifier. The application verifier is a free utility from Microsoft that works with Visual Studio to enable you to test your applications prior to production release using a very strict runtime environment. In our test application, we set up a 16-byte character buffer, and then we iterate through that character buffer, setting each of the values to 0. But you'll notice that based on our for statement, we're actually going to iterate well beyond the end of it, and this execution won't end until we finally get an exception by trying to set memory we don't have access to. So if we go ahead and we start in debug mode, now this is without application verifier. We've allocated memory data, and we'll take a look at that in memory. Now you see we've got 16 bytes here. It starts off with these 4 FD bytes, and we've got the 16 CD bytes, and then 4 more FD bytes. Now we're about to run through, and I'm going to tell the application to continue, and we'll very quickly get an unhandled exception. And when we break, we can see that we went 984 bytes into that array until it finally told us that we weren't allowed to write anymore. So if we were to say at the location data, we were to scroll down, you'd see that we'd have to go very, very far and be able to write over a lot of data before the runtime would actually know that something was wrong. So we're going to stop debugging now, and this time we're going to run, and we're going to use the application verifier. By using application verifier, the first thing you'll notice is when we allocate the memory of data, it's treated a little differently. First, we still have the same leading FD bytes and then our actual buffer memory that we can work with. But then after the trailing 4 FD bytes, there are 4 D0 bytes. These are used to indicate when you've read over the end of an array. So as soon as you try to get past that, reading or writing, it's going to throw an exception. So in our case, what we'll do is we'll continue execution, and you'll notice we immediately get, first of all, a more clear heap violation detected error, which is much easier to work with, and it explains that has to do with our allocated block, that we either overran it or underran it. And if we break, you'll notice that it's at 24. So this happened very, very quickly. In fact, it happened as soon as it reached the end of, in our case, the D0s that were here. As soon as it tried to write to this location, the exception was thrown. Now in our case, we got pretty lucky there because we don't have memory in here that we were particularly worried about losing. But now let's take, as another example, what if we were working instead with reading memory? Well, here we have very similar code, only this time we're reading, and you'll see we actually get the same behavior when we start in debug mode, in that we can run through, and eventually we'll get an exception, in this case 984 bytes in. But if we were to run this using the application verifier, it would not only tell us what happened, but you'd see it would stop at 24 bytes in, even though we were only reading. It's very important because at runtime, you want to be sure that your application is going to succeed. And by using application verifier, you're able to get a much higher level of confidence in your code. One other topic inside the advanced buffers arena that we're going to cover today is string formatting. Methods like printf and sprintf typically take a format control string. That's the highlighted string shown in these 3 examples. It's a string that includes text that you want to have either formatted or sent directly into a buffer, and it also includes, typically what we have here are the %d, %p, and %s specifiers, as well as a whole other array of format specifiers and characters that can be used. For a C++ developer, you'll know that %d means that it's going to be an integer value, %p is the pointer, and %s tells you that it's going to be a string. And each one of those refers to the parameters that are being passed into the function directly after the format specifiers themselves. What happens when these methods get called is that rather than having a predefined set of parameters, they work in conjunction with a built-in variable argument mechanism that allows you to send more than one or two or any number of parameters into a function, and then the callee function will be able to pull those off the stack and apply them to the method as necessary. This is primarily used in string manipulation routines such as printf or sprintf. It's important to keep in mind, though, that there is no way to really type check this. So if you were to pass in a string that had multiple percent characters in it, such as %s, 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 that would indicate to the method you're calling that it should pull 3 variables off the stack and expect those to be the 3 parameters to the method, and then use those in some meaningful way. So it's often to be careful about how those strings are passed into the methods because they are never validated by the callee function itself. So some of the risks that kind of pop into front of mind is if you're not validating the format control string, who is? And the unfortunate truth is that nobody is validating it at that point. So with an example like the sprintf code that's on the screen now, the user input would be passed directly into the method as the format control string. Now, for a long time, it wasn't believed that these could be dangerous, but it turns out that the strings can be used in a combination with unexpected stack variables, which could have to do with variables that were passed into methods that were in the call stack, or perhaps even created on the stack earlier on. Now, in many cases, these bugs will result in functional bugs or maybe crash the application. But it is important to know that it is possible to have malicious exploits that can take over control of the machine and run arbitrary code. To give an idea of how new these bugs are as a classification, it's while they've been known about for a long time, they weren't considered especially serious until around the year 2000 because most people were unable to find a good scenario in which you could exploit the code. But it's actually been something that's grown more and more over the past few years and is something that developers really need to be aware of. In addition to your standard C++ style string format risks, there's also importance to keep in mind the potential risk you'd have in managed code where you still take in format specifiers, usually with variable indexes wrapped in braces. And while those won't necessarily give an opportunity for a malicious user to have a elevation of privilege, they can still perform denial of service by causing exceptions to be thrown, and if those exceptions aren't caught, the application can be taken down. So as we had talked about, there are multiple types of threats that are available. The first type we'll cover here is information disclosure, and that's where you print stack information to the console or potentially to the log in the case of an sprintf that'll be eventually moving to a log. In most cases, that's not particularly relevant. However, there are combinations of ways to use this where you could either get access to information on the stack, or even worse is you could have private data itself being held in stack variables that get printed to the console or to the log or out to a socket connection. The second type of risk to be aware of are denial of service risks, where you can reliably crash a target application. Of course, those are available in managed or native code, so it's a pretty universal risk anywhere that you use a format specification mode. Finally, the elevation of privilege is always going to be a risk here because you can execute arbitrary code. Similar to the buffer overruns, you can use a string format bug in a creative way to write over the instruction pointer that's used as the return from a function. Now let's take a look at a string format bug in action. In this demo, we're going to take a look at how a string format bug could be exploited in order to take over execution flow of an application. You'll notice that in this application there are only 2 methods on the screen right now. The first one to be called is foo. Foo takes in a character buffer for an address and a character buffer for user input. All it does is allocate a 164 byte length character on the stack, and then it calls into this foo2 method, passing the address parameter, the buffer it allocated, and the user input parameter. Inside foo2, it prints a simple message to the screen, and then it actually takes the buffer from user input 1 and puts it into buffer for 2, rather for the parameter number 2, which is also called buffer. Now, when we run through the execution of this, what you're going to end up seeing is that this sprintf here will go and pull values off the stack all the way down to this address, which is a parameter to the method. It will grab the value that's at that address, and it's going to write it so that it overwrites the return pointer from foo. So we'll take a look at this in action quickly. And you'll see we first started off, we've already gone into foo. If we see from the call stack at this point, we've called from winmain into foo2. And now in foo2, we have our user input. Now you'll see the user input here is a bunch of carefully formatted format specifiers. So we have 8-byte hexadecimal characters that are going to keep getting pulled off the stack. You notice it's very, very long. And then the very end of that is actually an address, which has been detected as being the return pointer from the foo method itself. So if we take a look at buffer here, now buffers was allocated on the stack, remember. So if we turn that into 4, what we can do is we can actually take this guy and we can scroll him all the way down. And eventually, if we were to write over him long enough, what we'd find is we reached a point where somewhere down here would be the return instruction from this method. So now, what we'll do is we'll go ahead and we'll step over this. Now we step over this string copy, which happens fine. We're going to step over again to return to the previous function. Now we returned fine here, but this is the case where if we continue running, the next thing that would happen will be we would end up hitting this "you have been hacked." So at that point, the bar method took over as the return address from foo function because our string print overrode all of that data all the way down to the bottom. So it's kind of tricky to take advantage of a string format bug, but you should be very aware that it occurs. Now the way to fix a bug like this would be instead of using the sprintf here and allowing this to be the string, which also includes format specification, you could simply replace this such that you said %s here or %limited s with a certain number of bytes allowed, and then pass this as a parameter. In review, it's important to be wary of using certain functions. Just like with the buffer overruns topic that we covered, pretty much any string copy method that you're going to work with, you need to be careful and be sure that you're passing the right parameters in, that you're checking the sizes, and that you're aware of the differences between the characters and bytes or the count versus size. We didn't cover the difference between Unicode and ANSI here because that was covered previously, but that is definitely a topic that could be a stumbling block if you're uncareful. Besides following buffer overrun protections that are important, it's valuable to use application verifier because during debugging you'll be able to find runtime bugs of when you overwrite a heap. And the nice thing about the application verifier is that you only have to overwrite a heap variable by 1 byte either before or after, whether it's reading or writing, before it will be able to throw an exception and make you aware that your code has reached a problem. There are probably many times out there when a developer's released code that only wrote over the heap variable by 1 or 2 bytes given the test paths, but then once it got out into the open, there were malicious users that found a way to take advantage of it further. And finally, always validate the strings you're going to use as format control for any kind of variable argument string methods. Typically, it's a good process to only pass in a %s as the format specifier if you're going to have a string that you want to print out to the screen or print out somewhere else. In the worst case, with a printf, somebody could pass in a bunch of %s's and %d's and print all kinds of garbage to the screen and potentially crash in a worst case scenario. So it is always a risk to be aware of.